Thank you, Roger, for the invitation. I'm going to loosely talk about global games with strategic substitutes. It's an ongoing work with my colleague, Rodrigo Harrison. So I will give a short motivation. I will talk a little bit about global games. Gabriel already did in the morning, so that will be fast, I hope. Then I will talk about expectational coordination, and then some results in strategic substitutes, and intuitions, most likely. So the motivation is that we have this table here, and if you think about complete information strategic complements, we know that you can bound the set of rationalizable strategies by equilibria of a game. And we know that if we have unique equilibrium, then that equilibrium is strongly rational under the definition that Roger gave yesterday morning. If you have strategic substitutes, then you cannot be as optimistic, but you know that the bounds for rationalizable strategies are rationalizable. But unique equilibria does not give you expectational coordination as you would wish. If you have an incomplete information, and that's where global games come in, what you usually do is prove that you have a unique equilibrium in the complete information game, and then you believe that as a coordinating device, right? Even if you had multiple equilibria in the complete information piece. So what we want to do is to see whether can we give some kind of result, like the one with strategic complements and incomplete information, or strategic substitute with complete information regarding uniqueness of equilibrium and strong rationality in the sense of Roger. So what we do is to study a class of global games, right? And we provide conditions to have uniqueness of equilibrium, and then what happens with this equilibrium being the only rationalizable solution, right? And I will look at global games as coordinating devices. That will be the motivation, right? So I will talk a little bit about equilibrium selection. So you have a complete information game. Payoffs depend on a parameter x, right? This usually has many equilibria for some subset of the parameters. And then what you do is you go to an incomplete information game about this parameter, right? Incomplete information about this parameter. And then what you care is to calculate the set of Bayesian Nash equilibria. And if pointwise on each x you have this convergence here, right, to subset of the Nash equilibrium, then you use that as a tool to select equilibria, right? So in most of the examples that I have seen, what you do is you have multiple equilibria, and then the Bayesian Nash equilibria gives you a selection of one of the equilibrium that you had. So you use it as an argument for coordination. So this is an illustration. In this game, if x is big, then you have only one equilibrium with a strictly dominant strategy. If x is small, you have the other equilibrium with a strictly dominant strategy. And if x is neither big nor small, then you have both equilibria are equilibria. So this is the picture. To the left, you have 0, 0 as equilibrium. To the right, 1, 1. And in the middle, you don't know what happens. But then you put incomplete information, and you can claim a result that says that with incomplete information, you will have a unique Bayesian Nash equilibria. And what is important for this to use it as a coordination device, right, is that the proof is made by iterative elimination of strictly dominated strategies. So you think that people are actually thinking about what the other guys, about what the other people should be doing. And the picture that you get is this, right? So you would say that to the left of 1/2, you would get the 0, 0 equilibrium, and to the right of 1/2, you would get the 1, 1 equilibrium, right? So I make a pause on global games, and
Pedro,
yes?
You have only spent 5 minutes on your talk.
Too fast? Okay. Is there any question? Okay, I'm sorry, I'm going too fast. Sorry? No, I'm Chilean.
I thought they are slow.
Chilean people? Spanish people? No, Chilean people are regular people. So I'll continue slowly. I make a pause. I give a definition of what we mean by rationalizable strategy, right? So if it's a characterization actually, but it's the one that we use here. So a strategy is rationalizable if it's generally if it survives iterative elimination of non-best responses. That's not true always, but in our context it will be true. I will look more to the iterative elimination of strictly dominated strategies, which is not a problem, since rationalizable strategies always survive this process. And since we're looking at uniqueness of equilibrium, if that if the game is dominant solvable, then you know that the unique equilibrium is the only rationalizable solution. So we don't lose information, or we're not doing something not as general as we would like. And then we have the definition of strongly rational equilibrium, which we would say that an equilibrium is strongly rational if it's the only rationalizable strategy profile, right? So we use this as an argument for the rational expectation hypothesis, right? Then you would say that if this is the case, then you would believe that people or the players or whatever the system that you're studying, the outcome of that should be the unique equilibrium that you have. Because in that case, the equilibrium, of course, will be unique. So I understand that we have some studies, Guesnerie and co-authors, and myself, we have a paper on this. In the incomplete information framework, I know that Stephen Morris is very interested, and he has published a couple of things, and he also has sent us, me and Rodrigo, some calculations, and we have discussed a little bit with him. And so I go back to this picture. So in all these cases here, in these two cases, you have a very good story, right? You have a uniqueness of equilibrium, so the equilibrium is strongly rational. Strategic complements is really a very nice world. If you have strategic substitutes, then it's not that nice because you may have a unique equilibrium, but this equilibrium may not be strongly rational, right? So in these two papers, there are results that give conditions to actually have this unique, that indicates that you had a unique equilibrium, whether this unique equilibrium could be strongly rational or not, right? And although I put this paper here in complete information game, it's a little bit unfair because it's a paper about this lattice game. So information is not relevant there. You can always put an incomplete information game in a lattice game context. So I think we should be careful about this one, but it's okay. So let's look at this part of the picture here. So we look at the global game with strategic substitutes. So the question is, what can we say about a strategic substitutes environment? So I will begin with an example. We have a simple game, right? People choose between 0 and 1. Those are the payoffs, which can actually be written in this matrix like this. And to simplify the exposition, I will show you a picture here. So this is the picture. Here we have X, and here we have the action of the players. So player 1 is black, player 2 is red. And we know that if X is small, then the unique equilibrium is 0, 0. If X is large, the unique equilibrium is playing 1, 1. And in the middle, we have two equilibria, but they play different actions. With strategic complements, in the picture of strategic complements, we had also two equilibria here, but the two equilibria were the equilibria that were outside this region, right? As Gabriel said in the morning, we call this part here and this part here dominance regions because players are sure about what they should do. And this, I will call it later the uncertainty region. So the problem with this uncertainty region is that we don't have any of the two equilibrium that appear in the dominance regions here, right? So this is 0, 1 and 1, 0. There's no 0, 0 or 1, 1 as an equilibrium. So the process that you do when you have strategic complements is hard to process in this case. Actually, you cannot do it in this particular example. You can do nothing about it. But if you change a little bit the game, so what I do is I add this kind of cost for the second player, and I will call this that players are now heterogeneous. I know that it's not the standard. I mean, when we say heterogeneous players, it's not exactly this what we mean, but I will call this heterogeneity. So basically, players are different. In that case, what you have is this picture. So in this part here, player 2 knows what to do, right? Player 1 does not know exactly what to do. And in this part here, player 1 knows what to do, and player 2 does not know what to do. But the beautiful thing is that now in this part, in the complete information game, we have a unique equilibrium. Sorry. We have a unique equilibrium, which is 1, 0 here, and it's also 1, 0 here, right? So our guess is that if we do some kind of iterated elimination, right, exactly. By heterogeneity, I mean that the players are different. This player has this cost. The players are exactly the same, but this player has a cost, right? So one would guess that if I try to do this global game exercise to select an equilibrium, the equilibrium that I should select is the 1-0 equilibrium, right here in the middle. So actually, and this is the picture, what you do have in that case, I mean, if you do the process of elimination and stuff, what you do get actually is a unique equilibrium, which is each player uses a switch, what we call a switching strategy. So play 0 if x is small, if your signals is small, play 1 if not. But the two players switch strategy, switch action in different points. Okay? So this is an example. And let me show you what the setting is. So we think of an n-player game parameterized by x. For each player can choose 0 or 1. And then they have a payoff. And the payoff depends on the player's action and depends on the other player's action through the aggregate, right? So the players care about how many people are taking action 1. So how many people are participating. You can think of this as, I think the main example is a public good. And so this is how many people are putting money for the public good, and this you receive a payoff that depends on how much you value the public good and whether how many people put money for the public good or something like that. Right? So this function here depends on 0, 1 here, and here only on 0, 1, 2, 3, and n minus 1. And the tool that we use is the gain of playing 1, given that n people are participating and that the signal is x. Okay? This is the gain of playing 1. So we will put some assumptions. The first one is strategic substitutes. So this gain of playing 1 is decreasing in the quantity of players that are playing 1. A continuity assumption, this is just technical. And then monotonicity, so this gain of playing 1 is increasing in the value of the public good, if you want. It's increasing in the parameter. We need to have the indifference points. These are the points that give you the dominance regions. So, for instance, this player I, if he sees x smaller than this, then player I will always play 0, because the gain of playing 1 it should be negative because of the others, and it will even worse if he uses if there are more people participating, and if he sees a signal here greater than this point here, then the player should play 1. And we add this. So this is the new part, which is that we need players heterogeneity. So players to be different, and by this we mean that we can rank the players. So there's an order of the players, and we will say that a player J will be greater than a player I if for both players observing the same value of x and facing the same n, then player J has less incentive to pick the higher action. So this is the setting, the basic setting. We go to incomplete information. These are standard assumptions. And the important thing for us is that with these assumptions, when a player receives a signal when player I receives a signal xi, then he can guess about the signal received by the other player, xj in this case, and he knows that that signal will be in this interval and has this distribution for guessing the other player's signal. So what is the first important result? We look at this strategy here. It's a switching strategy. Player I will play 0 if the signal is smaller than a certain threshold, 1 if it's greater, and this threshold satisfies this equation here, which says that the gain of playing 1, so the player I is indifferent between playing 1 or 0 when I minus 1 players are playing 1. Okay? That defines xi star. And the result is that this strategy, so each player playing a strategy like this, gives you a unique variation Nash equilibrium if your sigma is sufficiently small. And so one could argue, as in the strategic complement case, with this theorem, that you can use this as a selection device. But I claim that you cannot do it, because what matters actually is the proof of the theorem for the complements case. The proof of the theorem is that you eliminate strictly dominated strategies. For the proof of this theorem, it's not enough. If you eliminate strictly dominated strategies, you cannot arrive to this equilibrium. You arrive to a bigger set. So the proof actually is a little bit intricate. Of course, there's no point of showing it here. But the point is that you cannot get to this by only eliminating strictly dominated strategies. So an equilibrium would look something like this, right? Here we have 3 players. The first player switches here, the second player switches here, and the third player switches here, right? So these points here should be for the third player where he sees he's indifferent when in this point. The third player is indifferent between playing 1 or 0 when he sees the other 2 players participating, which they are actually doing, right? So here he jumps from 0 to 1, and then he plays 1. That's an example for the thresholds. So the question is, okay, we have a unique equilibrium in this framework, but do we have a strong irrational equilibrium? What can we say about that? And for that, I will consider this space here that I call the uncertainty region, right? So these are the dominance regions. The dominance regions are not exactly the same for all the players because players are different. But this region here, no player knows what to do, right? There's no dominance in that region. So one intuition says if dominance regions were smaller, the uncertainty regions were smaller, maybe it should be easier to get the unique equilibrium by eliminating strictly dominated strategies, right? To make this uncertainty region smaller, one possibility is to decrease the distance between each player's dominance region, right? So to decrease the distance between, for instance, this k bar here and k bar 1 here, right? If I decrease this distance as a modeler in the model, right, as a parameter of the model, then my intuition says that it should be easier to get the unique equilibrium that we know it exists. Another way to do it would be to, given that not looking at this distance between dominance regions, we could talk about players' heterogeneity. So for instance, if players are more heterogeneous, then this point should move to the left and this point should move to the right, and that would also decrease this region here, right? So it should be also an optimistic, I should be optimistic on the possibility of getting this unique equilibrium by only eliminating strictly dominated strategies. So what we have done is to add to those 5 assumptions, right, the ones that set the game, to add this assumption that says that players are sufficiently heterogeneous, where on purpose, I leave sufficiently heterogeneous as something ambiguous because, in fact, Rodrigo and myself, we don't really know what that should mean, okay? And the result that we would like to have is that if we have the 5 assumptions that give uniqueness in the case of strategic substitutes, and we add this hypothesis of sufficiently heterogeneous players, then this unique point that we know that is unique, this unique equilibrium, then it is the only rationalizable strategy profile. And in that case, we would be able to use, we would be allowed, if you want, to use this model, a model that satisfies this hypothesis, as a coordination device or as an equilibrium selection device in the complete information game. So as I said, we don't really know what sufficiently heterogeneous should mean. We have a couple of equations here that actually in the models that we have studied with 2 and 3 players are the same equation. So look, this is the uncertainty region, right? So the k bar up bar for 1 minus down bar for n. This is the uncertainty region. This is a number that multiplies it. And then here we have the distance between dominance regions of the players. But the thing is, we really don't know what sufficient heterogeneous may mean in a general context, okay, and general players. For 2 or 3 players, we are able to give precise conditions, which should look like this, actually, and we may call them as sufficient heterogeneous to have the result. So what I'm going to do now is to sketch how we do it for 3 players, okay, but in a very general context, because we think that the idea here, which actually comes from the strategic complements case, you saw something similar to this in Gabriel's presentation in the morning. So I want to show you how we do it, right? So we define these sequences, X bar for each player, upper bar and lower bar. And the thing is that on each step, we know what a player would do, so a strategy that survives iterative elimination of strictly dominant strategies. We know that it may take any value in this interval, okay? But we know that outside this interval, the strategy should take the equilibrium strategy value, whichever it is, okay? Gabriel, I think Gabriel mentioned this as an infection effect, you said? Right, infection effect. So we say that this sequence here is increasing and this one here is decreasing, right? And that's the infection effect. Since this is going down, at each step we know what players is doing for greater signals. This one is going up, so we know what each player is doing for lower signals. And what you have to prove is that these two sequences collide, right? They crush each other, and then what should happen is that they collide and then they stay constant. But actually what happened there is that you find a unique strategy, and it's the equilibrium strategy. So that's what we actually do as modelers. But here I would like to say what is going on behind this. Okay? So what is actually being done? The actual thing that is being done is the following. These sequences here are generating a series of strategy profiles, S lower bar and S upper bar, such that any profile that survives these steps of the elimination is between these two profiles. Of course, there's a lot of assumptions, right? Well, not assumptions, but I am putting here less or equal, so you have to believe me that you can actually rank profiles. You can compare some of the profiles. But what you know is that any profile that survives these steps will be smaller than this profile that we're generating and greater than this other profile that we're generating. When you work with this profile, in one step, the profile increases. That means that it increases. It means that some zeros in some values of x where you played 0 here, now you will play 1. Okay? And this sequence here decreases, which means that for some values of x where here you played 1, now you know that they actually play 0. Okay? So you see that S in between the two for any t, and this is decreasing, this is increasing. So it looks a lot like the x's, but you're looking at strategy profiles. This is, I put this only to say how you would get one profile from the other. Basically, what you do is to get the lower bar profile. What you have to do is to look at best responses of the upper bar profiles of the previous iteration. Okay? That's all. For the upper bar profile, you look at best responses of the lower bar profiles. Okay? So it's a canonical thing in strategic substitutes. And then, what you would like to have is that the condition of repetition implies that these two profiles collide in the equilibrium profile. Okay? And that is exactly what's going on when you're looking at the x's. Okay? So at the sequence of x's that you study when you're doing the proof. Why is this relevant? Because this process here is the exact process that we studied with Roger in a general case, not of incomplete information, but with a continuum of players and an aggregate value. So it's the exact same exercise, and it's also the exact same exercise done by Simperl in his paper. That has nothing to do with global games. So we see that strategic substitutes are repeating in some way here also. It's the same exercise, although one would have thought that it's somehow different. So this is what the picture would look like. We start with that. We begin fixing the profiles for the players from below. Then you fix the strategy profiles for the players from above. And in the limit, what happens is that you fix all the profiles for all x, and what you get is the unique equilibrium. So this was my comment. In these two papers, we know what we can find bounds for rationalizable outcomes, and these bounds are cycles of order 2 of a best reply mapping. I have not talked about the best reply mapping in this case because in a general situation, it's hard to say what a best reply mapping looks like in the incomplete information game, in the global game, right? But you have these two results. You know that when you're working with that in the examples, 2, 3 players, what you're doing actually is something like this. And so intuition says that you could use this result, so the following result. If the second iterate of the best reply mapping has a unique fixed point, then you have a unique equilibrium and it is strongly rational. So one thing that we would like to do is to use this kind of result in order to have the strongly rational equilibrium in a global game of strategic substitutes. Right? Actually, this framework that I showed may be set in the Simperl framework, but of course we don't know exactly what comes out. I mean, how to work with it. Okay? So just some comments to finish? Okay, some comments?
You started very quickly, but you more slowly.
So now you know why I started quickly.
But you are in time. So
Okay. So we have global games to take substitutes. It's an open question what happens there. If you add player heterogeneity, then you can have a unique equilibrium as in strategic complements. But this equilibrium is not necessarily strongly rational. We have done some specific models with 2 or 3 players, and we have this conjecture, if you want, that if players are sufficiently heterogeneous, then the equilibrium should be strongly rational. So you could use the global game tool, right, as a coordination device, as an equilibrium selection device. We know that this is true for 2 and 3 players, but we need to translate this sufficient player heterogeneity assumption for more players, more n players, of course, and for more general payoffs. So that's what we're doing now, right? And we think we're doing quite well. We will get something soon. I hope so. I don't know if you have any comments.